Okay, so today we're looking at some more basic rules of probability, but extended off of what we spoke about earlier in the week. Okay? The four rules we talked about earlier were basically just playing off of the idea that everything that's possible needs to add up to 100%. With this one, now we're starting to look at other cases and also extending that third rule that talked about disjoint or mutually exclusive events and adding their probabilities together. The probability that this or this happens, we had said or means add, and you can simply add them together. Okay. Now, I will say we're going to be doing a lot of math in our section today. So what I would recommend, if you want to look at these notes that I have on Canvas and work some of these problems out there, or get a split screen going so that you can watch and listen and write at the same time, or at the very least get some paper out and work out some of these problems, because this is not one of those lessons that we've had recently where you can just kind of sit back and watch. We need to be doing some of this stuff. Okay? So our targets for today, we're going to be talking about, yes, I will post the recorded version of the lesson. We'll be talking about independent events, which are different from mutually exclusive. And that's a big thing that we need to pay close attention to, those differences. And we'll kind of hammer that home coming up later. We're going to be looking at probabilities of non-mutually exclusive events. Okay, rule 3 was if you had disjoint or mutually exclusive. Well, what if it's not? Okay. We can still accommodate that pretty easily, but we have to be aware of those modifications. And lastly, we'll be looking at conditional probabilities. That's probably something we'll be examining on Monday in our next lesson. Okay, this is kind of a longer one. We're starting to build, and I want to make sure that we take some time to go through example problems together. So we're extending it out across 2 days. So here are our 4 rules that we had started with on Monday. And we had said that how 3 of these rules were actually all kind of the same thing, saying that everything that's possible needs to add up to 1 or 100%. And we used that 4th rule to use a complementary probability that if something does not happen, we can subtract away the probability that it does happen from 1 and get that resulting outcome. Now, the 3rd rule, we had said if A and B are disjoint events or mutually exclusive, then you can add those probabilities together. The key word there being or. Or means add. Now, this was if they did not overlap one another. Let's think about seniors in our high school, seniors who are taking a math class. You're given a decision. You can take some form of a calculus class, okay, whether that be AP, regular calc. There's that CHS business calculus that Mr. Kaufman offers. Maybe some of you are taking that. Or you could also take statistics, okay, whether it's this class or AP statistics. Okay. Most of the seniors take one or the other. Okay. But these are not disjoint. There's overlap. There are some students, maybe you're one of them, that's taking both stats and calculus. So we can kind of visualize this with a Venn diagram. Okay, you're familiar with this. If we had a disjoint set of events, then they're completely separate. Okay, no overlap between them. We see that down here with A and B. Okay, they both fit this sample space, or sometimes that box around is called the universe, but they're completely separate from one another. So if you wanted the probability of A or B happening, you can add those two. But if they are not disjoint and there is overlap, like we have in our second case, this region here where there's overlap has been counted twice. If we add all of A together and all of B together, that overlap has been counted twice. And that could mean that you're exceeding 100%. Okay? So if we took it back to our example of the students here, everyone taking statistics plus everyone taking calculus, well, those stats and calculus students, they've been counted twice. So we can make an easy modification to our equation and just subtract away that overlap so it's not counted double. Okay? Now, if you were just learning a single equation, this would be the one to go with. The probability that A or B happens for any two events, whether they overlap or not, is the probability of A plus the probability of B minus the probability of A and B. If they were disjoint and there was no overlap, this probability of A and B is 0. So you're subtracting nothing, and it becomes that simple equation that we looked at in our previous lesson. Okay? So this is just a slight adaptation to our addition rule for different events, if they are disjoint or if they are not disjoint. Any questions on that so far? All right. Let's try an example problem here. Let's say we're going on a picnic and we take a cooler, and there are 20 bottles in this cooler made up of 8 Cokes, 5 Pepsis, and 7 waters. We reach blindly into this cooler, okay, not looking, and only pull out one bottle. We want to know the probability of choosing a Coke or a Pepsi. Well, when we're selecting one bottle, okay, we can't have Coke and Pepsi at the same time. So these are disjoint events, and we can just add their individual probabilities together. Probability of Coke is 8 out of 20. Probability of Pepsi is 5 out of 20. And then our resulting probability, 8 plus 5, is 13 out of 20. Easy enough. Another example here, let's say there's a class where there are 12 boys in this class, and that's made up of 8 seniors and 4 juniors. We also have 8 girls in the class, made up of 3 seniors and 5 juniors. We are interested in the probability of selecting a boy or a senior. All right, so there's that keyword or means add. But in this case, this process of picking a boy and picking a senior, they are not disjoint. Okay? They can obviously occur at the same time. If we pick a senior boy, that's a simultaneous selection. We're only picking one, but it fits both categories. So in this case, we want to follow along with the equation and subtract away any probability of overlap. Now, we have to fill in some blanks here because from the numbers that we were given in our description up here, we don't really have the full picture just yet. And we did see that there are 12 overall boys, 8 overall girls. Let's make this chart down here to kind of organize what's going on. We had said that there were 12 boys. Of those boys, 8 were seniors, 4 were juniors. And 8 total girls, 3 seniors, 5 juniors. So this gives us an overall total of 20 students in the class, and we can add across horizontally to get the total number of seniors, 11, and the total number of juniors, 9. Now this is helpful when we start to analyze this with the equation. The probability of choosing a boy or a senior, the probability of picking a boy, there were 12 boys out of 20 students in the class, so 12 out of 20, plus the probability of selecting a senior. From our horizontal addition, we said there were 11 seniors out of 20 students in the class. But if we look at this right now and ignored that these were not disjoint, 12 plus 11, we're at 23 out of 20 students in the class. This probability exceeds 100%. We know that that cannot happen. And that reason is we've counted senior boys twice. Okay? We need to subtract away the overlap that a selection is both a senior and a boy, of which there were 8. So that probability is 8 of the 20 students in the class that we're removing. We had said 12 plus 11 was 23. 23 minus 8 is 15. And to show off our math skills, they reduce this here to 3/4, even though I said yesterday that's not an emphasis of this unit for us. Now, I went into a little bit more detail here than you would do every single time, but I think it kind of illustrates how you can organize your thinking and process, okay, what you have, what are you interested in, how do you get that answer that you desire. Any questions so far? Okay. Let's try this next question here. It says we have a pizza shop that has 2 sizes of pizzas, large and a small. And on a certain day, this pizza shop made 59 plain pizzas and 72 pizzas with toppings. Of those 59 plain pizzas, 19 were small. And of the 72 pizzas with toppings, 42 were large. A pizza is chosen at random. Find the probabilities. Make a chart. Okay. We don't want to just go into this problem without organizing our thinking. Okay. We had the chart provided for us on the last problem. It won't take long to make. Let's take the extra 60 seconds and make this chart to organize what's going on. So we have large pizzas and we have small pizzas. We also have a total row that we're going to make. Going across the top, we either have plain pizza or we have toppings. And once again, we have a total column. Now, we have this laid out. Let's substitute in the values that we know. It said the pizza shop made 59 total plain pizzas. So 59 plain pizzas. 72 of the pizzas they made had toppings, so those go in the total row. Now, be careful here, there's an indicating word of. Of the 59 plain pizzas, 19 were small, and of the 72 pizzas with toppings, 42 were large. So of these 72 topping pizzas, 42 were large. A pizza is chosen at random. Find the following probabilities. Now, if we didn't make this chart, we'd have a little bit of trouble. Maybe some of these 9 questions we'd be able to pick and choose some that we could answer. But by finishing this chart and filling in the blanks, we will be able to answer very easily all of these problems. Okay, so let's finish this, right? We had 59 total plain pizzas. They're only available in large or small. And if 19 of them were small, 59 minus 19, we have 40 large plain pizzas. Similarly with the toppings, 72 total, 42 are large. Subtract that away. That leaves us with 30 small topping pizzas. And we can add horizontally to get our totals. We have a total of 82 large pizzas, a total of 49 small pizzas, and add vertically or horizontally here. Carry the 131 total pizzas. Okay. Now, we can go through and answer. We're not going to do all 9 of these down here, but look at this. Probability that we randomly select a pizza, and that's a large pizza. Well, there were 82 large pizzas out of 131 total. Okay. Small, 49 out of 131. With toppings, 72 out of 131. And plain, 59 out of 131. Letter E, a large plain pizza. Now we're getting into the breakdown here, okay? Let's look at this chart and analyze it once more. Okay. We have this center box. This is called a contingency table. It's a 2x2 contingency table that we will revisit and look at a little bit closer later in the year. But on this table, inside that purple box that I just drew, you have every one of those 131 pizzas falling into one of those four quadrants. Okay. The other numbers are all totals. Okay. So inside that box, you have every one of the 131 pizzas. So a large plain pizza, just match it up, row and column, 40 of the 131 pizzas. Down below, let's look at letter G. Here's where we see that word or. What's the probability of a small or a plain pizza? You could do this a couple of different ways. Okay? Go with me for a second, even if it's not the way that you would initially do this. A small pizza. We have a total of 49 small pizzas. So let's start adding these here. 49. You could put it over the 131 right now, but let's just go with the numerators. Or plain pizza, we have 59 plain pizzas. Okay? So 49 plus 59. We can add those together because we know that or means add, and we have 108 pizzas. 108 pizzas out of our 131. But there is overlap here. We have small and plain occurring at the same time. In fact, we have 19 of them. So there's the overlap that we need to subtract. That's a 5, by the way. So subtract away these 19. Okay, and this leaves us with our final answer, okay, of 89 out of 131 total pizzas. Right? We add the two together, subtract away our overlap, and that leaves us with our final answer. Now, that might be a little bit of overkill that you wouldn't originally want to do the problem like this. Okay. Looking at our chart, we do have some options. Okay. We could go with a different method if we wanted to. And some of these are just kind of process of elimination. Okay. If I want small or plain, and everything that's possible needs to be inside that purple box, well, small or plain, okay, 19 is favorable. These are small pizzas. Okay, going over to plain. These are plain pizzas. These 19 are also plain, but I've already highlighted those. I don't want to do that again. So I can just add up these three highlighted values. 40 plus 30 is 70, plus another 19 is 89. Put it over our overall total of 131. There's our final answer, 89 out of 131. Or maybe you're looking at this as, okay, if there's a small pizza or a plain pizza, that's my favorable outcome. The only thing that is undesirable is a large pizza with toppings. That's the only thing that I don't want. So I could go back to my fourth rule of basic probability and say, take away from 100% what I don't want and do 131 minus 42. Lo and behold, that leaves us with 89 out of 131. Okay. Now, you've seen this before sometimes with like algebra class. There's multiple ways to do a problem. And sometimes you can get away with like finding a method that works for you and just always going back to that method. Okay? I would suggest with probability that even if you have a favorite method, be aware of these other techniques, because what's going to happen is you'll be presented with some information that lends itself to one method over another, or might make some of these other techniques impossible, if not really difficult. Okay, so instead, you want to be familiar with what you could do. Personally, I kind of like the chart and just doing what I talked about at the end here. Okay, pick the 3 values that are favorable, or take the one thing that's unfavorable and subtract that away from 100%. I don't really want to use this equation if I don't have to. But if I didn't have that chart available, or it was impossible for me to make the chart, then I'm certainly going to be using that equation. Okay, so you do want to know what options you have available to you. Questions here? Yes, Selena?
For letter E, why is it over 131 and not 82?
So for letter E, you'd said?
Yeah.
Because you're looking at a large plain pizza. The 82 that you had were just the total number of large pizzas. So the wording becomes very important, and we'll see more of this when we talk about conditional probability on Monday. If I had phrased it as like, given that you have a large pizza, what is the probability that it is a plain large pizza? Then it would have been 40 out of 82. But the way that it's worded, I mean, it doesn't directly say the overall total, but I think it's safe to say the assumption is we're talking about all pizzas, of which there are 131. What's the probability that we randomly select one of these 131 pizzas? What's the probability that it is a large plain pizza, of which there are 40? Okay? All right. So, shifting gears a little bit, let's start talking about multiplication. We've been looking at adding different events together and their probabilities, if they're disjoint or not disjoint. This multiplication principle is a very, very fundamental idea that we probably could have and should have thrown into our lesson on Monday. Okay? If you can do a task in m number of ways and a second task in n number of ways, then the number of ways that both tasks can be done is a times b ways, or m times n number of ways. Okay? We have an example here that rolling a standard die and flipping a coin, okay, we have 6 outcomes on a die, 1 through 6, and we have 2 outcomes on a coin, heads or tails. So we can multiply those two together, 6 times 2, to get 12 total possible outcomes. And if you wanted to visualize this, you could. Okay, with our coin flip, let's say we have heads, we could have that paired with a die outcome, heads and a 1, heads and a 2, heads and a 3, etc., all the way up through heads and a 6. Or maybe our outcome is a tail. Tail and a 1, tail and a 2, tail and a 3, etc. Okay? But this quickly, we don't need to look at all of those possibilities every single time. We're really just concerned with how many possibilities are there. So that leads us into a couple of example problems here. And these are pretty easy. The soccer team is silk screening t-shirts. They have 4 different colors of t-shirts and 2 different colors of ink. How many different t-shirts can be made using 1 ink color and 1 t-shirt? Okay. So this is as easy as 4 shirts times 2 inks. We have 8 different possibilities. Okay, thanks to that counting principle. Our second example here, a travel agent is offering a vacation package. participants choose the type of tour, a meal plan, and a hotel class from the table below. Right? So we can take either a walking tour, a boat tour, or a bicycle tour. For our meal plan, we can have restaurant meals or picnic meals. And we can stay in either a 4-star, 3, 2, or 1-star hotel. So we don't really care about what the options are. We're just concerned with how many of them there are, and we're multiplying them together. So 3 tours, 2 different meal plans, 4 different hotel options. 3 times 2 is 6. 6 times 4 is 24 different packages. These are the basics. This is probably probability that you've already seen before. Okay? But it lays the groundwork for independent events. And this multiplication rule directly ties into probabilities. Okay? We were just talking about the events themselves. We can also multiply probabilities together. And if these events are independent, okay, it will equal the probability of both of them happening simultaneously. Now, independent is one of these words that it has 2 different interpretations. Okay? One of them is a verbal interpretation, meaning that if 2 events are independent, then they do not influence each other, or knowledge about one does not impact the likelihood or the probability of the other. Now, that's a good enough definition for our general purposes. However, we will be seeing problems where we are asked to justify that 2 events are independent or show that they are independent or not independent. And we can't just say that one does not impact the outcome of the other. No, it's not that easy. You can't just say it and then that's proven. We have to show that it's true with this equation here. Okay? This is the mathematical definition of independence. 2 events are independent if you can multiply their individual probabilities together and it equals the probability of both of them happening. Okay? So, let's take a look at a couple examples. Okay? Talked about coin flips are independent. Okay? Dice rolls are independent. If I flip a coin, that first outcome of heads and tails, that has no impact on any subsequent outcomes, right? I get heads my first flip. That second flip doesn't make it more likely to be tails. That is a big misconception about human reasoning. And we talked a little bit about casinos the other day. Okay? That's why people go to the casino and lose a boatload of money, is because they think that, well, I've had a little bit of a string of bad luck here, but I'm due for that luck to turn around. Okay? It doesn't work like that. That's one of the biggest flaws of human reasoning, is this misunderstanding about independent events. Okay? If I flip a coin and I get 5 heads in a row, okay, that's not terribly probable or terribly likely, but that does not make it more likely to get a tail on my next flip. Okay, those coin flips are independent of each other. Okay? We have an example problem right here that a woman is planning on having 2 children. Assume that the outcome of the second birth is independent of the first, and that is shown to be true. Childbirths are independent of each other, meaning that if you have a boy the first time, that does not make the second child more or less likely to be a boy or a girl. Okay? And the probabilities of boys and girls, they are very, very close to 50-50. Okay? Close enough that we'll usually just assume that they are. But if you look at the numbers, it is slightly more probable that a given childbirth will result in a boy than a girl. And Scientists have kind of debated this, but the overall conclusion is that because men tend to die at an earlier age, the thought is that nature kind of balances itself out by making an individual childbirth slightly more likely to be a male than a female. Okay, because the females live longer. So, rounding these probabilities, let's say that the probability of a boy is 51%, probability of a girl is 49%. Okay? The probability of a woman having a boy followed by a girl, we can multiply these probabilities together, 0.51 times 0.49. We get a number very, very close to 25%, 0.2499. Okay? So it's about a 25% chance that a woman will have a boy, then a girl in that order, because they are independent events. Okay? Now, again, we talked about the misconceptions of things like this. Like, because childbirths are independent, like sometimes people will think that like you have two girls, okay, that if you're going to have a third child, that couple is due to have a boy. No, it doesn't work like that. It's just as likely. And this is kind of hitting home because my wife and I've told some of you, but we're expecting our second child. We have a girl as our first one. We found out about a week ago that our second child will also be a girl. And we're excited about that. It'll be nice to have two girls that are like pretty close in age, about 2 years apart. My wife is due in April, but at the same time, I can kind of admit that I wanted a boy. And we'll see if we want to and are able to have a third child. If we were to try for a boy then, but who knows? I mean, again, it's like flipping a coin. You don't know if you're going to get a boy or a girl. Okay. And we'd be thrilled either way. Okay. But it's kind of illustrating that it doesn't affect those probabilities. You have independent events. Now, at the bottom of this slide, we see here that proving independence can be difficult. Okay? It gives you an example. Is making a second foul shot in basketball independent of the first foul shot? This is debated back and forth by both like sports people and mathematicians and people who kind of overlap in that area. Okay? The general consensus is that foul shots, where you're minimizing other factors and influences, they are thought of as being independent of one another. Okay, assuming that like it's not some end of game scenario where you're intentionally trying to miss to grab a rebound and stuff like that. So you're trying. Okay, foul shots are thought to be independent of one another, but you can't just go back to that verbal definition of one impacts the other or it doesn't impact. To show independence, you need to satisfy this equation. And this equation, I'm going to give you a little trigger warning here with, we're going to have a geometry flashback. All right. This equation is a biconditional statement. And if you remember from geometry, freshman geometry, biconditional statements are true both forwards and backwards. So typically, we are using this equation for independence as probability of A times probability of B equals the probability of both of them happening. But if we're testing for independence and we have this probability that both of them have happened, then we need to illustrate that it is equal to the individual probabilities to prove independence. Let's go back to our senior boy example here. Okay? Are choosing a senior and choosing a boy independent? Well, from our chart, we had said that the probability of selecting a senior, there were 11 seniors in the class, that was 11 out of 20. and the probability of selecting a boy was 12 out of 20. So you multiply these together, reduce your fraction. 11 times 12 is the 132. We know that 20 times 20, or 20 squared, is 400. So 132 divided by 400 gives us 0.3. But the probability of selecting a senior boy, that overlap, if you recall from the chart, there were 8 senior boys in the class. 8 out of 20 is 0.4. These are not equal to each other. So because they are not equal and they do not work in this equation, they are not independent. Okay? And this is how we illustrate this. This is how we prove this, by showing that it either works or it doesn't work in this equation. You will have questions like that. And it asks, are they independent? You can't just say yes, move on. You can't say no. You have to show it mathematically using that equation. Questions about that? All right. Shaquille O'Neal was a really good basketball player, but not a very good free throw shooter. He has one of the worst career free throw percentages of anyone. I'm not a big basketball person, but I know that his career free throw percentage of 52.7 was not that good. If you're talking about like a good free throw percentage, I mean, somebody correct me if I'm wrong here, but I'm pretty sure it's like in the 80s, or if not close to 90% of those free throws that you make, if you're a good, really good free throw shooter. So back in his playing days, let's say he was fouled and he goes to the line to shoot 2 free throws. We want to calculate what the probability is that he will, in part A, make both of these free throws. So this is going off of that free throws are in fact independent of each other. So that 52.7%, we're going to treat this as a decimal, and the probability that we make that first free throw, 0.527. And because they're independent, we can multiply the probability that we make the second free throw, also 0.527. So 0.527 times itself, which is like squaring it. Rounded to 3 decimal places, this is 0.278. So he goes to the line. There's about a 27.8% chance that he's going to make both of those free throws. Any questions on what happened there? Now, letter B asks for the probability that he will miss both of these free throws. Sometimes what I'll see is that students will have done part A, 27% chance that he makes both of them. So they think that, well, he either makes or he misses. I can just subtract that 27% away from 1, and there's about a 73% chance that he'll miss them. No, that is flawed logic here. Because you have these independent events, we have scenarios where you're mixing and you can make one but miss the other. And you can see we're going to get into that in letters C and D. So what we need to do, if it's a 52.7% chance that he makes a free throw, we need to apply that logic of a complement, but with an individual free throw. 1 minus 0.527 gives us the probability that he misses a free throw, and that's 0.473. Okay. So there's a 47.3% chance that he will miss a free throw. Now, kind of like what we did in part A, we're going to follow this same procedure. He misses the first shot. Independently, he misses the second shot, 0.473. Multiply these two values together to get the probability that he misses both shots, and we get 0.224. Any questions so far? All right, so letters C and D. This is kind of what we were anticipating. Our alternative option is if he were to make exactly one of the two in any order. And kind of looking ahead even further, notice the differences between question C and question D. Make exactly one, make at least one. Okay. We'll think about how these two variations differ, but it underscores the idea that the wording is very important in probability. Okay? Make sure that you read very carefully in these problems. All right, so the probability that he makes one of the two, well, let's just play this scenario out. The probability that he makes that first free throw, 0.527, and then he would miss the second one, times 0.473. We can multiply this out. 0.527 times 0.473 is 0.249. Now, if you look at all of the probabilities that we've done up to this point, about a 27 or 28% chance that he makes both, about a 22% chance that he misses both, about a 24 or 25% chance that he makes one of the two. This does not add up to 100% just with a quick glance. And the reason here is that the order matters. This calculation that we just did was that he makes the first one and misses the second. We also need to consider that he misses the first one, 0.473, and makes the second one, 0.527. Now, obviously, you're going to get the same answer, 0.249. Multiplication is commutative. It doesn't matter if you do A times B or B times A. You're going to get the same answer. However, both of these answers need to be considered together. Because let's think about what's going on. A successful outcome in letter C is making the first, missing the second, or missing the first, making the second. Or means add. We add these two probabilities together to get our overall probability. 8 carry the 1, 9. There's a 49.8% chance that he will make exactly one of the two in any order. Okay, make the first, miss the second, or miss the first, make the second. Any questions here? And at this point, if you were to look at all of our answers that we have, oops, change to a different color here. This value plus this value plus this value all add up to 1. And we could have also obtained this answer in letter C by subtracting away our two answers in A and B. If we had done 1 minus 0.278 minus 0.224, there's our answer of 0.9 or 0.498. We probably could have done this from the very beginning, but let's look at everything that's possible. Okay. Let's say that if he makes it, it's good. We'll put a G there. If he misses it, it's no good. We'll put an N. We have two outcomes for each shot. He either makes it or he misses it, going back to our multiplication counting principle. So we could have a letter A scenario where both the first and the second are good. We could have a letter B scenario where they're both no good, or a combination. The order is important. Okay? We have 4 possible outcomes when we're shooting 2 free throws. What we did is this was our answer in letter A, This was our answer in letter B. These combined were our answer in letter C. Letter D says, what's the probability that he makes at least one of the two in any order? So this change in the wording, let's think about what a desirable outcome is. Making at least one of the two would mean that letter C is favorable. We have this 0.498, or he could make both of them. So we have this is favorable, and this is favorable as well. Or means add. We can add the 0.278 to it. So we're adding our values together here. I probably should do this by hand, but I'm feeling lazy on a Thursday morning, and I want to make sure that I'm right. 0.776 is the probability that he makes at least one of those two, which would mean one or the other, or both. Or you could also flip this around and interpret this as the only undesirable outcome is that he misses both of these free throws. And if that's what I don't want, I could subtract this probability away from 1 minus that. You can kind of see how the numbers are going to work out. You're going to get that same exact answer. Okay. So think about how these basic rules play off of each other. Okay. They don't exist in a vacuum. They exist together. And I said that, like, independently, yeah, the rules are pretty straightforward. But as we progress with probability, we want to be able to use them together to get fairly complex answers. Any questions right now? Okay. This is a good stopping point. So we're going to pause right here, and we'll get into conditional probability in our next lesson on Monday. Now, you do have that homework assignment from the book in chapter 12 that you have due tomorrow morning. Okay? I had mentioned that yesterday. Please make sure you take care of that. That is your priority in terms of assignments in this class. I do have an additional basic probability homework too, kind of like that sheet that we'd had earlier in the week. I don't have this next one due until Wednesday morning, okay? But it is available on Canvas now. You cannot do everything on it just yet because we haven't talked about conditional probability yet. But if you wanted to start looking at it, you might be able to do a couple of those problems. Well, maybe like the first problem on that probability practice, okay? But there's no rush. I just wanted to make you aware of it. After Monday, we'll talk about conditional probability. We'll do more practice with this together, and we'll get really good with it. Long-term planning. We're going to be taking a quiz on probability, not next week, but probably the following week. So without ironing down a date for sure, probably looking at like Thursday, December 17th as a quiz, not a full-blown unit test, because we're going to have more after winter break that we want to do. But we'll be looking at a quiz coming up December 17th. Okay. All right. Anybody have any questions? Good day, and I'll see you on Monday. Okay. Take care of that homework. Get it submitted. Bye.